Good day, ladies and gentlemen. My name is Ed Button. I'm the training officer for Ampere. We're going to start off with Module 1 to explain the function of the refrigeration cycle. First of all, we have an evaporator. The evaporator's function is to remove heat. Second point, compressor. The function of the compressor is, of course, to absorb, to compress, and to release. Our third function, or the third point in the system, is a condenser. The function of the condenser is to release heat. The function of the whole system is comprised of a heat exchanger and, of course, an evaporator. The compressor's function, as mentioned, is threefold. To change the system from high to low, we need to have, of course, a TEV, or a thermostatic expansion valve. We're going to cover that in a little bit a later stage in our other modules on the function of a TEV. From our evaporator, we would have a refrigerant vapor coming in. All right, the arrows indicate the flow. So we have vapor coming into the compressor. As mentioned, and as everybody has seen in previous videos, that vapor entering the compressor is critical. We cannot have any liquid entering the compressor, as this can damage the compressor. No compressor or any compressor cannot function under a positive load, meaning a liquid load itself. From the compressor, it will be pumped into the condenser. Once again, guys, I'm pointing out in a arrow format. This will be in a vapor form as well. Okay, but remember, our temperature coming out of the compressor, whereby the vapor has been compressed into a high temperature, high pressure. This means we could most probably sit with at least 30 degrees on the condenser side itself. From the condenser, it would flow through the coils, as mentioned previous videos as well, and the coil will provide the exchange from a vapor to liquid. This means any vapor form that's in a high pressure, high temperature will condense back into a liquid. If we take, for instance, a spoon, by placing a spoon in front of a kettle spout while it's boiling, it condenses against the spoon surface. The spoon surface is much more colder than the vapor coming out of the kettle spout. This means the temperature difference between the two surfaces is such in a great, enormous state that it changes to a liquid state. This we call dew point. So the dew point is the amount of vapor comprises onto the surface of an object, whereby it starts condensing to droplets. From droplets, it turns into liquid. Now, this same function that is taking place over here takes place within our condenser. The condenser provides a dew point section whereby it changes from a vapor state to a liquid state. We like to mention that at least anything from 50% to at least 70% of the condenser changes back into a liquid form. Once we have liquid exerting the condenser into the TEV, so between our condenser and our TEV, we have a liquid. The liquid passes through the TEV, through the orifice. So just to give you guys an example of a TEV itself. The TEV comprises of different subjects, different parts onto the system itself. On top we have our diaphragm. This part over here would have our capillary tube, which will be attached to our feeler bulb. Inside we have a spring, and this spring is allocated to a diaphragm. Once the diaphragm operates. Now, the diaphragm is filled up with a liquid substance. That liquid substance is very changeable with temperatures itself. Once the temperature and the liquid substance expands, it pushes the spindle, as you can see, this rod or this needle all the way down, and it pushes the needle and seat at the bottom. It pushes that through, creating an expansion. So to understand this a bit more clear, if you take your spray, like a can of Doom or your bathroom spray or scent, that small nozzle on the front part itself creates a mist. So in the container that you have, we've got liquid. But once it passes through that small area there, it creates an expansion. That expansion changes into a vapor form. So to understand this clearly, we're going to remove this part over there. As you can see, our function over here, we have the needle itself over there, and we have the pin. So by pushing the pin in over here, as you can see, it moves, all right? By moving this pin, we can create the refrigerant liquid that passes through this part over here. By passing it through itself into the orifice part expands it from a liquid state to a vapor state. That vapor state passes through our filter. It's got a filter attached to it as well. This is just to prevent any uncondensable substances that may enter, preventing clogging into the orifice itself. As you know, the orifice is quite sensitive to any variable changes into the refrigerant cycle itself. This fits, of course, it slides in at the bottom. As it slides in at the bottom, it goes all the way up, as you can see there. It goes all the way up, fits snugly, and then the vapor passes through over here. So the TEV creates a high pressure liquid substance to a low pressure vapor substance. Now, always remember that passing it from the TEV to the evaporator, we do not have 100% vapor. We have anything from 80 to 90% vapor. This vapor must pass through the evaporator coil. As it passes through the evaporator coil, at least I would recommend anything from 50 to about 60% of the evaporator's capacity. It changes from a 80 to 90% vapor to 100% vapor. We like to call this section superheat. The superheat that is attached to this means that once the refrigerant vapor passes through the evaporator, it adds heat to the coil. It absorbs the heat to the coil. This means any substances that's been placed within the box. Remember, a box is a cabinet or a space that needs to be cooled. So a box can be called a room, for instance. It can be called a refrigeration compartment. So we like to use the terminology box because a box is in generally covering most areas that can be cooled. So the box area would have fruit, it would have milk, it would have meat which is being stored for a limited time period itself. Thereby, the heat that's inside the evaporator's cabinet, the box, gets absorbed to the evaporator, all right? And as it gets absorbed to the evaporator, our liquid refrigerant vapor that passes through this. Now, during this cycle, as vapor passes into the evaporator cycle, we have liquid substance, larger molecules, and we have smaller molecules. This is what they call about, we've got more vapor and we've got less liquid. But the liquid substances are in droplet forms. Once the liquid droplets come in contact with heat, it changes to 100% vapor. All right. So this means that once the system is running perfectly, all right, that means our system will have temperature changes taking place. the compressor will be in operation, and then our TV will function correctly as well. A TV is adjustable. Just refer back to our unit itself. The TV is adjustable. We can actually remove the spindle on the side. By removing the spindle, it have an adjustable screw at the back. And by adjusting the spindle or the adjustable screw, we can create that this diaphragm be pushed up more or less. Thereby, turning it in all the way, we're creating less refrigerant, we're creating less refrigerant entering the evaporator. By turning it out all the way, we're creating more refrigerant entering to the evaporator. The terminology used in this case, we would of course, by turning in the spindle all the way, we're starving the evaporator, meaning that there is little or no refrigerant entering the evaporator. Then, by turning the spindle all the way out, means we're flooding the evaporator. This means we have too much refrigerant liquid entering the system and bypassing the proper sequence that needs to take place. This is critical, whereby we need to do adjustments correctly onto the spindle. This means our temperature difference from entering and our temperature difference from exiting must be anything between 5 to 7K difference. We're going to speak about this in a later module as well, to do your settings on the TEV. On top of that itself, a TEV can be identified through the information that is displayed onto the TEV. The older TEVs used to have color codings onto the top of the diaphragm, whereby there was a sticker that was placed, and the sticker would actually identify what refrigerant is inside the system. But due to time, it normally gets rubbed off, or the sticker gets lost, or the sticker gets damaged as well. You cannot identify what refrigerant or the color itself. So in recent days, I would say at least for the last about 10 years, they started to actually embed the information onto the panel itself, onto the diaphragm body itself. Thereby, it cannot rub off. It permanently stays in that position itself. So this is a TEV. And as you can see, the TEV's inlet, it's much smaller than an outlet. This is a 3/8 flared joint, and this is a 5/8, a half-inch flared joint itself. You get different sizes TEVs for different applications itself, and we'll have a look at that at a different module as well. Thanks, guys. We appreciate your interest in this. As mentioned, if there are any additional information that you would like to inquire, you're more than welcome to contact us directly on my cell phone number. It's 0812091441, or you can email us at edward.button@ng.com. Thanks, guys. This is our first module. We will proceed with the second module, and we would like to explain a bit more pertaining to the refrigeration cycle on how the system comprises together. So our second module that we would implement is the physical evidence. We've done it via our drawing. Now we would like to do it physically and show you the evaporator, the condenser, and where all these parts are allocated. Thanks, guys. Have a lovely afternoon, and speak to you soon. Thanks. Bye. Stop video. Stop recording.